Okay, here is part 2 of the introductory material for chapter 14, where we're going to get a little bit better understanding about these multiple center MOs by looking at a particular molecule, that being butadiene. Alright, but first, a step back. Conjugated alkenes. What do we mean by these conjugated alkenes anyway? Because if we have conjugation, that means we're going to be looking at multiple center MOs. Orbitals that can extend over several atoms simultaneously. Well, conjugation means there's a p orbital on each adjacent atom. It may be empty, it may be full, it may be partially full. But each adjacent atom has to have a p orbital on it. So, is this a conjugated system? Well, clearly, there's a p orbital on each adjacent atom right here, right? Just looking right. That's got to be sp2, that's got to be sp2, that's got to be sp2, that's got to be sp2. This is not a conjugated system. Why not? Well, conjugation means that these adjacent p orbitals must be able to overlap, which means they must be in the same plane. And clearly, these two are not in the same plane as these two. So there's no way these two can overlap. They're at 90 degrees to one another, so this would not be a conjugated system. Now, the conjugation and multiple center molecular orbital thing explains, right? We saw that in the last mini lecture. But what does it explain? Well, it explains butadiene, and we're going to look at that in some gory detail in this little embedded video here. So,
alrighty, so I'm going to talk to you a little bit about butadiene, as it is an example that helps us understand why multiple center molecular orbitals are a reality. So here's butadiene. As you can see, we have two double bonds separated by an apparent single bond. This particular conformation of butadiene is called the S-trans conformation because it's zigzag, so it seems like these guys are trans to one another. But seeing as this is a single bond, we ought to be able to rotate freely around that C2-C3 single bond and have multiple conformations of butadiene. And in fact, the other extreme would be the S-cis conformation, where it kind of looks like we have a cis arrangement of the two double bonds. But here's the rub. It turns out that the rotation around that C2-C3 single bond is really tough. It's like, I barely can move these apart. So that doesn't make sense. If this is a regular, if C2-C3 is a regular single bond, it should be pretty dang easy to rotate around that bond, and it's not. What that is telling us is that that bond isn't a full-fledged single bond. It has partial double bond character. And the reason why is because the p atomic orbitals on each of the carbons that overlap to make these double bonds are actually distributed across all four carbons in the conjugated system. In other words, there's one molecular orbital that gives C2-C3 partial double bond character. That helps explain why there's this hindered rotation in the C2-C3 bond of butadiene.
okay then. So, butadiene can't be explained, or at least these properties of butadiene can't be explained unless we understand the molecular orbitals that are involved in its structure. The hindered rotation, the fact that it prefers to be planar, either S-cis or S-trans, and S-trans is the more stable conformation, and the fact that the C2-C3 bond is not a normal single bond. It's all about orbitals. Alright, so let's do the same thing we did in the last mini lecture, which is look at our molecular orbital energy diagram. We have four atoms, each of which has a p orbital, so that means there's four atomic orbitals that are going to combine to give us four molecular orbitals. What will they look like? So we can again anticipate that the most stable molecular orbital will be fully bonding, and that will be psi1. The least stable will be fully antibonding, like so. So this is really high energy, totally unstable. Let's look at some nodes here. Psi1 has one node, and psi4 has 1, 2, 3, 4. 4 nodes for psi4. So clearly psi3 and psi2 are going to have 2 and 3 nodes respectively. So what do you think they'll look like? Well, let's just do it. There's our 4 p orbitals. How are they going to be arrayed so that I end up with 2 nodes? Well, it seems to me that this is the logical arrangement for psi2, 1 node here and 1 node here. And remember, we have to stay symmetric, so for psi3 we could have these two overlap. So I do have the ability for these guys to overlap in the middle, but then otherwise I have 3 nodes. It's kind of a messy drawing, so why don't we look at the real deal. What does Gaussian say these look like? I'm going to skip ahead here. There are the 4 molecular orbitals for butadiene. So psi1 fully bonding, psi4 completely antibonding, and then our 2-node psi2 and our 3-node psi3. So going back, what I've shown on this molecular orbital picture that I've erased the orbitals on is basically that these energy level differences for psi1 to psi4 of butadiene are kind of smashed closer together than the pi and pi star molecular orbitals for ethene. So remember that ethene's non-delocalized molecular orbitals would just be the pi and the pi star. And of course, ethene's pi system has 2 electrons, and they would both be in this HOMO, and the pi star would be the LUMO, unoccupied and lowest energy. Well, what about butadiene? How many pi electrons does butadiene have? Looks to me like butadiene has 4 pi system electrons. Therefore, what we're looking at is this kind of energy diagram, molecular orbital diagram with the electrons being filled into the lower energy molecular orbitals first. So that makes this guy, psi2, my HOMO. And remember that that was this guy. And my LUMO then would be psi3, because it doesn't have any electrons in its orbital. So here's my LUMO. So that's kind of butadiene in a nutshell. The fact that you have one orbital that, well, actually that's not true. You have 2 orbitals, psi1 and psi3, that clearly show C2 and C3 as linked together by molecular orbitals. That makes C2, C3 shorter. It prevents rotation about C2, C3 because you can't, that will rend the molecular orbital. So molecular orbitals explain everything, just about. So here you go. Your next step. Can you do the same thing Now, not for butadiene, but for something even more complicated, a conjugated system with three conjugated double bonds. The MO diagram for 1,3,5 heptatriene. That's what you should try next. And you should think about what you should be able to do by now, which is basically you should be able to explain what a multiple center MO is and how that's important for explaining electron delocalization. And then be able to draw these MOs. Draw them just the way we have for the last two mini lectures, this one and the last one. But before you do that, an important question: how much do pirates pay for their earrings? Well, obviously, $1 an ear. Yeah, okay, that's it. All right, see ya.